In the previous video, we looked at how to integrate the CANopenIA module into a board design. The next step is to configure the module, which we will look at in this video. Out of the box, the module operates as a digital and analog I/O node, and it can be used in a standalone mode to connect inputs and outputs to a CANopen network. However, a robot arm doesn't fit into that scheme, so we need to create our own custom configuration and use it as a coprocessor. To do that, we will use CANopen Architect. More details about our editor can be found at CANopenArchitect.com. We will start with a template project for the CANopenIA module. This contains some required entries to support the module's functionality. The first step is to create some manufacturer-specific object dictionary entries. As we are controlling stepper motors, we will need the following pieces of data for each motor or axis. Send a new target position, get the current position, and get the status. If we use the analogy of a C language struct, we would group all of these items together into a single axis or struct, and then have multiple structs in an array. We can do the same thing in the object dictionary. First, we create a new entry for a single axis, and we will call this x-axis. The entry has 4 sub-entries. We want the target position to have a resolution of 0.1 degrees, and although we can use floating point values in CANopen, it takes 4 bytes of CAN message data to transfer. It is more efficient to multiply the value by 10, and it can then be stored in a 16-bit integer. We want this entry to be readable, so we can always get back the current target. In the comments field, we enter a helpful description of what this entry contains. The sub-entry for the current position is identical to the sub-entry for the target position, except it is read-only. It doesn't make sense to be able to write to the current position. The final sub-entry contains the status. This is a bit field, and we will use 2 bits. Bit 0 is set when the current position entry is valid, and bit 1 is set when the axis is at the target position and therefore not moving. We will use an 8-bit storage type because we may want to use more bits in the future. Now we have an entry for the x-axis, we can copy and paste to create the other 5 axes. Each axis has a different range, so we need to update the comments field so it is correct. Port 0 on the module needs to be configured to use the serial functionality, also called remote access. We do that by setting entry 5F01, subentry 1, to the value 6. We want the module to output a heartbeat message once a second, so we change the value of entry 1017 to 1000. If we go to the device commissioning section, we can set the node ID and bitrate to the values we want, in this case 10 hex and 125 kilobits per second. The next step is to create the PDOs, and we have to think about how we want to be able to interact with the robot arm, what makes the most sense. First, let's look at what data is transmitted. We have 6 axes and each has 1 byte of status, so we could put all of the status information on a single transmit PDO or TPDO. We can put all of the current positions into a single PDO, but we can split them into 2 groups. First, we create a TPDO for axes X, Y, and Z. Now we create a TPDO for axes A, B, and C. We set the inhibit time of the current position TPDOs so that an axis is a partway between the 2 positions, it doesn't flood the bus with messages. Now we will get a TPDO on the bus whenever an axis status or position changes. We can watch for an axis reaching a target position and know when to send the next target. We can supply new target positions by writing to the object dictionary entries we created, but that is inefficient and doesn't allow for coordinating motion. We could achieve both by mapping the target position entries into receive PDOs or RPDOs. Like the current position, we can't fit all of the entries into one PDO, so we'll split them into the same 2 groups, therefore creating 2 RPDOs. If we were using CANopenFD, then PDOs can be longer and we wouldn't need to split the axes into groups this way. We need to enter some descriptive information. To do that, we go to File Information and enter a description and some comments. We also need to go to Device Information and add a product name and order code. At this point, we are ready to export the configuration to a binary file. The next step is to use the CANopenIA download utility to transfer the configuration to the module. Now we can open CANopenMagic and see the bootup message, confirm the node ID is correct, and that the heartbeats are being transmitted. More details about CANopenMagic can be found at CANopenMagic.com. As a final step, we can export the documentation for our module. We will use a Word document template. Select it by going to the Preferences and clicking on the Export Documentation tab. Now we can perform the export and view it in Word. From there we can tweak it, print, save as PDF and share with third parties. At this point, the module contains the object dictionary entries we need but no data. For that, we need to access the module from the host, and we will look at that in the next video. Thank you for watching.